Oh my God, there's so much people. Okay. Hello, can you guys hear me?
Yeah.
Okay, that's good. So the mic's working. The mic might cut off because the battery might die. Just let me know in the chat or through the voice chat if it dies, and then I'll just switch to the MacBook thing. Yeah. Okay, so the plan for today's session is to go over the topics that people requested for me, which is Baeyer-Villiger, and then let's go over the D2 exchange mechanism and the synthesis problems with carbon restrictions. Okay, so, okay. So for Baeyer-Villiger, reaction, right? We're gonna react this with a carbonyl with some kind of peroxy acid, RCO3H, right? And that's gonna give us either an ester or a carboxylic acid, right? So this peroxy acid, an example of that would be something like MCPBA, right? So the migratory list for the Baeyer-Villiger reaction, what Pascal gave you guys is tertiary is higher than secondary, which is higher than primary, which is higher than the methyl group, right? Where let's say, for an example, we have a carbonyl here, and then we have this R group and this R group here. We see that the R groups are going to be this R group here and this R group here, right? This is the carbonyl carbon right here. What this reaction would do is insert an oxygen between the carbonyl carbon and the highest priority group. So when we look at this R group over here, right? This carbon here is going to be tertiary because you ignore the bond to the carbonyl carbon bond. Ignore that bond and see how many other carbons this carbon is attached to. It's attached to 3 other carbons, 1, 2, 3. So that's a tertiary carbon group, right? This carbon here is bonded to 2 other carbons, so that's a secondary group right there, right? And based on this migratory aptitude list, the tertiary group takes priority over the secondary group. So what we're going to do is insert an oxygen in between this carbonyl carbon and that tertiary group right there. So this is the product we get right here. Right, where this is the ester that we get right here, where that's the new atom in that molecule. That oxygen inserted is up between that carbonyl carbon and that tertiary carbon right there of the group, right? I highly doubt the mechanism of this reaction is going to be tested, so let's just skip that, right? Unless you guys want to go over that. 32. Oh yeah, I am at the basement at the library right now. Is it loud or is the mic canceling the background noise as well? Can you guys like hear me like well?
Yeah.
Okay. Yeah, that's good. That's good. Okay. So, okay, you just want to go over the mechanism. Okay, let's go over the mechanism. Okay. So for the mechanism of this, it's going to be like this, right? Where, let's say we have a carbonyl and it has 2 R groups, R1 and R2. I'm going to circle R2 to represent that R2 is the higher priority group.
It's right there.
Right. And so I'm going to do MCPBA right here, right? Where I'm going to predict the product first because that is easier to do than drawing out the mechanism. Since R2, I said was the higher priority group, we're going to insert an oxygen between that carbonyl carbon and the R group right here. So that's the product that we get right here, right? Yes, there are seats around right now here at this table. So you can join if you want in person. Yeah. Okay. Oh yeah, Tanya's here too. So Tanya's answering the questions on Zoom. Yeah. So here's the mechanism. Right. instead of using MCBA, let me use something more general, which is RCO3H. Right. Okay, and this RCO3H will look something like this. Let's say this R3, right? This is a peroxy acid, which is a strong acid. The strong acid here is going to protonate this carbonyl oxygen and kick out that conjugate base right there. Once we do that, we're going to activate this carbonyl here. Right. Once that's activated, we can now use as a conjugate base that got kicked out with the negative charge to then attack this carbonyl oxygen here and then pop the double one onto the oxygen right there. Right. Now,
I just had it drawn.
once we do this, yeah, what was okay, so I'm going to redraw this product here into this form right here, right? Where I'm going to draw the R1 like that. This is that carbonyl carbon that got attacked. This is the R2 right here. This is the high priority group, which is this high priority group right here. Right? This is going to be the OH group that got popped up to become neutral right here. This is the new bond between this oxygen that attacked that carbonyl carbon right there, and this oxygen here is bonded to this oxygen, which is bonded to this carbonyl and R3 group right here. But I'm going to draw the carbonyl next to this hydrogen right here, right, with the R3 right there. Yeah. Okay, so this oxygen here is partially negative, and this hydrogen here is partially positive. They are going to have an attraction between each other because this hydrogen here is bonded to an electronegative atom, which makes it a very partial positive atom, right? Where there's going to be an H bond attraction between them, where this oxygen here is going to make a bond with that hydrogen using one of its bonds right there. This bond between oxygen and hydrogen is going to make a double bond right there. We're going to do this weird migration step. So, oh, hey, Amar. Yeah, no one's saying that. You can sit there. Yeah, great. So, we're going to do this weird migration step here, where since this is the high priority group, this is the bond that we're going to migrate and put that bond onto the oxygen right there, right? And then this bond between the two oxygen is going to break and make a double bond between that oxygen and carbon right there. So to keep track of everything, this is what I like to do. I like to number this atom number 1, this is number 2, this number 3, this number 4. This
They're going to say
5.
no. That is going to say no.
Right here, right? Once we do everything, R1 is bonded to this one oxygen right there, right? And then this is the oxygen right here that's bonded to that R2, where this is the atom 1, this is atom 2, this is atom 3 right there, and that's the R2 that migrated right there. This is the ester that we got right here. It's the exact same thing, right? And this side product here is just going to become HO1O R3, a carboxylic acid. That's not important. You don't have to write that as the product for a particular product. What's the point is this thing here, where the oxygen inserted itself between the carbonyl carbon and the high priority group, right? The weirdest step here is this migration step here, right? So that's the whole mechanism for Baeyer-Villiger. Are there any questions on this? Oh, let's just chat. Let's see. I don't know. Yeah, if you're on campus, I recommend coming to the basement physically. So like it's more interactive and you can ask questions here. Yeah, but you could also watch the Zoom as well. This will also be recorded and uploaded on YouTube. Yeah. Why did MCPBA added oxygen between the R2 and carbonyl? So MCPBA is a type of peroxy acid like this, right? Where the oxygen comes from the peroxy acid here, which is this oxygen right here. The new oxygen that we added is this oxygen here of the peroxy acid. And MCPBA is a type of peroxy acid. Is the high priority group the more substituted one? Usually, for Pascal, just think of it as more substituted. Don't think about like hydrogens, phenyl, cyclohexane. Yeah, right. Usually it's more substituted. Can you go over conjugated reactions with like O or N? Okay, conjugated reactions. Oh wait, let's go over your question first, like the D2 exchange, right? Yeah. Okay. Yes. Okay. Let's go. Okay. D2 exchange. Say. So when we have this carbonyl here with 3 alpha hydrogens, 1, 2, 3, and we react this with D2SO4, right? This is not H2SO4. So when we do this whole reaction here, let's do D2O as well. Let's say this gets, this is like, we're gonna substitute all of the alpha hydrogens into deuterium ions, like this, right? D, D, D. So here's the mechanism. This D2SO4 is like H2SO4, it's a strong acid. It's going to protonate the most basic atom here, the carbonyl oxygen. Yeah. Right. Makes the enol because this is protonated, and we can't say OH because we grabbed a deuterium. Right. And positive charge right here. And then let's draw out one of the alpha hydrogens. That alpha hydrogen is going to get deprotonated by the conjugate base that we formed to create the enol here. Right. So that tautomerizes the carbonyl into the enol first. Right. Now, once we have this enol here, the nucleophile is going to be this alpha carbon right here. So when we reform that carbonyl, we're going to use this alpha carbon to attack another deuterium from D2SO4, right? And that's going to pop up there and give us this right here, where now that alpha carbon has one deuterium because it attacked that deuterium right there. And we can't make that invisible because it's not hydrogen. It's an isotope of hydrogen, which we have to explicitly draw out in the mechanism, right? And then this oxygen will get neutralized by getting deprotonated by the conjugate base, right? Where at this point here, we substituted one of the alpha hydrogens into the deuterium here. We still have 2 more alpha hydrogens, which we're just going to repeat that whole mechanism that we just did 2 more times to substitute all of the alpha hydrogens into the deuterium there, right? Yeah. Can you guys still hear me? Okay, thank you. Let's see. Conjugated reactions with oxygen or nitrogen. Conjugated reactions. Like conjugated diene with HX. Oh, I think I know what you're talking about, like with the enone stuff. Right. Okay, let's go over that. Okay. So let's go over this. This is a new material, which is this is going to be on the test. The stuff here, the enone reaction with the hardest soft nucleophile. Okay. So let's say we have this structure here, when you see an alkene right next to a carbonyl, this is an enone. You could think of it as an alkene right next to a ketone, right? And there are two possible electrophiles here. One electrophile is going to be this carbonyl carbon right here. Can you guys think about the other atom that might be the electrophile? The beta carbon, right? And which one would be a stronger electrophile? Which one has a bigger positive? The beta one, right? And the reason why is because when we draw resonance, we are going to get this resonance structure here, where we could clearly see why that beta carbon is more electrophilic. There is a full positive charge on that beta carbon. There is no full positive charge on the carbonyl carbon here, no full positive charge on the carbonyl carbon there. But there is still a partial positive charge on that carbonyl carbon just because of inductions. It's attached to the electronegative oxygen right there, right? But the beta carbon here has a bigger partial positive charge like that, right? Where soft nucleophiles will attack the beta carbon. Hard nucleophiles will attack the carbonyl carbon, right? And when we number this, we usually number this as the atom 1, 2, 3, 4. So when you have a hard nucleophile attacking the carbonyl carbon, you might see that as a 1, 2 addition, right? Because we added the second position there. If you see a soft nucleophile attacking the beta carbon or the fourth carbon, then that's called a 1,4 addition. Or you might see it as a conjugate addition, because this is a conjugated system here with that oxygen right there. Conjugate addition. Okay. The easier list to remember is the hard nucleophile. There are two sources of hard nucleophiles, a hydride source, H-, and an R- source. The two hydride sources are the reducing agents, lithium aluminum hydride, sodium boryl hydride, NaH, right? All of these are H- ions here. The strong organometallic sources are Grignard, R, Mgx. It could be Br or chlorine, but usually Br, or organolithium, Rli. Right? If you see any of these acting with an enone, right, then it's gonna attack the carbonyl carbon right there. So for predictive product, always look for this structure here, enone. Don't always attack the carbonyl carbon just like we did in other reactions. That's a common mistake people do. Just because there's an alkene right here next to the carbonyl, you have to now consider if it's a hard nucleophile or a soft nucleophile, right? Because that will change where it attacks. Right. Because every other nucleophile, like enolate, enamine, organocuprate, bigumin, those are soft nucleophiles that will attack this beta carbon here. So soft nucleophiles are like the enolate, enol, enamine. It could be organocuprate with the R2, copper, lithium, and every other 118A nucleophile, Cn-, N3-, OR-, OH-, right? But you'll most likely see the enol, enolate, enamine, and organocuprate for this chapter. But the nucleophile for enol, enolate, and enamine is not the electronegative atom here. It's not oxygen or nitrogen. The nucleophile is going to be this alpha carbon here. Right? And that's because when we do resonance, the alpha carbon with the negative charge is less stable than the negative charge on the electronegative atom. And if it's less stable, it's more reactive, more nucleophilic, right? Which is why these are the nucleophiles that would attack the beta carbon of the enone right there. So this is a common predicted product question and mechanism question as well. Yeah.
Go over one of Pascal's synthetic questions.
Oh, shoot, with the ring?
I have the key for it.
Yeah. I want to try it first without the key and then see my thought process of it and then see if I get it right. Yeah, let's see.
Like, I was able to kind of like what reaction was on, since they drew it I was trying to visualize
I know, yeah. Thinking about the 3D stuff is hard. Okay. 1B on the practice midterm, it says hexane 3-dione as an incorrect. Okay, that question got answered. LDA. So yeah, so another hard nucleophile could be strong nitrogen minus charges or bases, right? So LDA could be, let's see. Actually, I'm not sure. Well, LDA is a strong bulky base, which is going to look for the most acidic hydrogen. And the most acidic hydrogen here is going to be this hydrogen right here, because compared to this alpha hydrogen right here, right? Do you guys know the reason it's more acidic than this hydrogen? This showed up on the practice final. This concept here. They have the same amount of S character because they're both sp3, right? Think about the conjugate base. Like if you put a negative charge here versus a negative charge here, what's more stable? Which one can do more resonance? This right one here, right? Because this negative charge can do resonance here, here, and here. It can hop around more. It can hop around more delocalized, more happy, more stable. Just up to the oxygen. That's it, right? Which is why this does not get deprotonated. If you have a strong base, this gets deprotonated here because it gives a more stable conjugate base.
The dots would go across that whole.
Oh, right. If we were to draw the thing, yeah, like a trail. Yeah, right. It would crawl all the way to the O minus right here. Right. And then the nucleophile here would actually be this alpha carbon right there. Because when we reform the carbonyl, that's the alpha carbon that would attack the electrophile, which showed up on the practice final, right? Which is like the RBR or RX, something like that. Yeah. On 4B in the practice term, the reagent base cat gives no reaction, but the key uses it as a reagent in the synthesis film. What is the difference? So I think yeah, it was a benzaldehyde, the reactant. And on the problem, is it the same reactant that you use or is it a different reactant? Let's see, uses as a reagent in the. Okay, let's just go over, explain that question first and then answer that question after. Let's see. Okay. Okay. So let's say we have this benzaldehyde here, and then we use some kind of base. For example, OH minus. Whenever we have an OH minus group, we always look for the strongest acid, the most acidic acid, which is usually an alpha hydrogen, but this is not an alpha carbon. There's no alpha hydrogen there. This is an alpha carbon, but that alpha carbon there has no alpha hydrogen because it already has 4 bonds, right? So we can't deprotonate an alpha hydrogen here. What people might think of is attacking the carbonyl, popping the double bond onto the oxygen right there, but that would create something called, right? Let's say this is O minus, this is OH, and let's say the O minus gets protonated by the water, the conjugate acid, right? This is a conceptual thing here. What is this functional group that we just created called? Where we have 2 alcohols on the same. This functional group called geminodiol, right? Because we have 2 alcohols on the same carbon, geminal. Math calls it a hydrate. Are hydrates able to be isolated or no? Not isolatable because it does not exist very long since it's very unstable. So it would completely destroy and go backwards here, right? So that's why there's no reaction. Nothing happens. If there was alpha hydrogen, right, then a self-Aldol condensation would happen, where we deprotonate that alpha carbon, generate the enolate ion, and then it attacks itself, another version of itself, to do the self-Aldol. But there's no alpha hydrogen here to deprotonate. But the key uses different reagent. Yeah, so that's the reason why there's no alpha hydrogen to deprotonate. So we cannot generate the enolate ion, no reaction. Can we go over Aldol self-mixed intermolecular? Yes. The first element where aldehyde ketones, we have NaH, but for some reason we. Okay, let's go over the Aldol first, and after that, let's go over the Baeyer-Jones one. Okay. Yeah. Yeah. Okay. So here's how to know if you have an Aldol reaction or not. Aldol condensation. Right, Mascal doesn't use dehydration, so we're just gonna assume condensation goes all the way through the enone. The nucleophile for the aldol is an enolate ion, right? Which is specifically the alpha carbon of the enolate ion. The electrophile for an aldol is going to be a carbonyl carbon of an aldehyde or ketone. Right. The product that you get is going to be an enone. Right? And there are three types of aldol. There's self-aldol, there's mixed aldol, and there's intramolecular aldol. So let's go over the self-aldol first, where let's say we have this aldehyde right here, and we introduce that with strong base, water, and heat. Whenever we have a strong base, we always look out for the most acidic hydrogen, which is this alpha hydrogen right here. Right? Once we figure that out and deprotonate this alpha hydrogen, we generate the enolate ion. Right? Where this enolate ion here, the nucleophile is the alpha carbon right there. Since this is self-aldol, we're going to bring in another version of itself as a carbonyl, which will act as the electrophile, right? Nucleophile is enolate ion, the alpha carbon. Electrophile is the carbonyl carbon of the aldehyde or ketone here. When we reform the carbonyl and use this alpha carbon to attack the electrophile and pop the bonds to the oxygen right there, this is what we get right here. Right, where this is the star atom, this is the dot atom right here. Then the next thing is to protonate this O- with the most acidic source we have, which is water. Right, but then we don't stop here at the aldol because we have heat, which to predict the final product, just get rid of the alcohol and put a double bond between the alpha and beta carbon, right? But the whole mechanism to do that is to deprotonate the alpha hydrogen in between the carbonyl and alcohol. And this is the boomerang step here, where it's gonna go up onto the oxygen and then later on it's gonna go back around and kick out the oxygen, right? So we wanna get rid of the alcohol. We wanna put a double bond right there, but we're not gonna do that directly. We're gonna do a boomerang step first, where we deprotonate the alpha hydrogen, make a double bond here, give that oxygen a negative charge to prepare to kick out that alcohol. Right? Now, this O- here comes back around to make a double bond, shift this double bond to make a double bond between the alpha and beta carbon, and then kick out the OH right there. See, it does like a boomerang kind of stuff. It goes there and it goes backwards to kick out the OH and form the new double bond to create this enone here. Right? This is an enone product of aldol condensation. Right. Okay. So for retrosynthesis, right? Whenever you see an enone as the product and then he tells you to go backwards, this is what you do. You first locate your alpha and beta carbon, which is this alpha and beta carbon right here. Then you make a cut between the alpha and beta carbon, where the alpha carbon here is going to be your nucleophile. That alpha carbon was the nucleophile enolate ion. The beta carbon is always the carbonyl carbon. That always came from the carbonyl carbon right there, right? So when we make this connection and go backwards, this is our nucleophilic alpha carbon, And this beta carbon here which is this dot carbon, I just added that carbonyl there because I know that that beta carbon was the electrophile, which we said is a carbonyl carbon, right? But in the mechanism, that oxygen there gets kicked out as an alcohol, right? So that's how you go backwards in retrosynthesis, where we notice that the electrophile and nucleophile are the same exact molecule, which is self-aldol because it's actually another version of itself, right? So that's why I showed you guys the spectrosynthesis, because when I go on to mixed aldol and then intermolecular aldol, I'm not going to do the whole mechanism again. I'm just going to go through the shortcut and predict the products there. Right. Okay, so now for mixed aldol, the nucleophile and electrophile are not going to be the same molecule, right? And I'm just going to give you guys the example where we only get one product, because I don't think Pascal's going to give you multiple products for predicted products. Let's say we have this benzaldehyde right here, and this acetone here in basic conditions. This strong base here is going to look for the most acidic hydrogen, which is going to be the alpha hydrogen here, right? So we already know that. Let's just start that alpha carbon right there, because that's the nucleophile. We know the electrophile is a carbonyl carbon, but we have this carbonyl carbon versus this carbonyl carbon right here, right? What is more electrophilic? What is more reactive? An aldehyde carbonyl carbon or a ketone carbonyl carbon? An aldehyde carbonyl carbon, right? Because this aldehyde carbonyl carbon here only has one R group stabilizing it, whereas the ketone carbonyl carbon has two R groups stabilizing it. Since the aldehyde is less stable, it's more reactive. So when we predict the product, this is what I do. There's always going to be a double bond between the star and dot atom, right? Where the dot atom will no longer have a carbonyl. So this is how you predict the product fast. Make a double bond between the star and dot atom, and then just attach what is attached to the star atom, which is this acetone there, which is our enone right there. That's how you predict the product without going through the whole mechanism. So that's mixed aldol there. Yeah, so to predict the aldol reaction quicker, locate the alpha carbon, which is the nucleophile, and store that. Which the nucleophile has to be this alpha carbon here because it has an alpha hydrogen that can get deprotonated and get a negative charge. Then you dot the electrophile, which is going to be the carbonyl carbon of the aldehyde here. Because this can never be the nucleophile since there are no alpha hydrogens there. Once you identify your nucleophile and electrophile, there's always going to be a double bond between the star and dot carbon, where at the dot carbon here, this carbonyl gets dehydrated. It gets kicked out as an OH. Right. So in acidic conditions, aldol condensation can still happen, right? But it won't be an enolate that attacks. It will be an enol that attacks. But you'll most likely see in basic conditions, so I wouldn't worry about that. But it can still happen in acidic conditions. Okay. Oh, thank you for answering other people's questions in the chat too. Yes, thank you. Okay, so let's think.
Wait, is this literally just one step?
Yeah. Okay, next question is to go. Oh, wait. Let's go over Amar's question, the retrosynthesis thing first, and then we go over the Wittig reaction. What the?
Yeah.
And the C5 limit?
Yes. I was having. I mean, I did see that you have like a 1.5 and a 1. It's like.
Okay. Yeah. Let's try this. Let's try this. Okay. Is this a carbon or is that a part of a bond? Like, oh,
Yeah,
connected.
it's connected.
Okay. Okay. I'm going to show you my thought process on how I think about this before I look at the key. What the heck? And then C5 limit. Okay. Okay, so the first thing I look at is what functional group we have in the molecule here. We have a carbonyl and an alcohol. Once you have that, I then determine what's the relationship between those two functional groups, right? Where I know this is going to be a 1, 2, 3, a 1-3 relationship with each other, right? Once I figure out the relationship between the two functional groups, I then determine what's the reaction that gives that 1-3 relationship, right? What reaction do you guys know that creates a 1-3 relationship? Aldol, right? This is going to come from an aldol reaction, right? Where the alcohol here came from a carbonyl, because for aldol reaction, like we said earlier, the nucleophile is an alpha carbon of an enolate or enol. The electrophile of an aldol is a carbonyl, right? Where when the carbonyl gets attacked, we pop that carbonyl onto the oxygen, which becomes OH there. So this is going to be my electrophile here. This is going to be my nucleophile here. That's my star. That's my dot. Then I make that disconnection between that star and dot right there. Okay. Let's see. Go backwards this way. What? This is so weird. Star. Now that bond is broken. We broke that ring. Now it's linear. But this is a bicyclic ring, right? We only broke one of the rings. We still have like a ring right here, right? And since I said that this is the electrophile carbon there, this electrophile carbon was a carbonyl carbon. So I'm going to make that dot carbon a carbonyl like that, right? Which is an aldehyde because we have one hydrogen right here. So I'm going to draw that aldehyde as like that. Okay, I'm going to redraw this because this looks very weird. Like this. I'm going to say this is my 1. Wait, actually, do a different color so I'm not confusing you guys with the relationship. 1, 2, 3, 4, 5. 5 carbon ring, right? Where all of the atoms in the ring are carbons. So let's draw that 5 carbon template ring like that. And let's say this is 1, 2, 3, 4, 5, like that, right? At carbon 4, we have a carbonyl. So I'm going to draw that carbonyl at carbon 4 like that, right? At carbon 3, I'm going to say that this is going down because this is going up. So I'm just going to put at carbon 3. But actually, it doesn't matter. We're just going backwards here. So it's attached to the CH2, CH2, and then an aldehyde like that, right? So do you guys have any questions on how I redrew this weird looking ring into this bond line form right here? Yeah, that's good. Good. Okay, right. I just numbered it 1, 2, 3, 4, 5, but that's the ring, and that carbon 3 is that whole R group right there, which is the R group right here. Now, once we do this, right, it's easy to see the relationship what's between these carbonyls here, right? Which is a 1, 2, 3, 4, 5. 1,5 dicarbonyl. That's the other relationship. What reaction do you guys know that makes a 1,5 dicarbonyl? Microaddition, right? We didn't go over this today, but what is a nucleophile of a microaddition and what is the electrophile of a microaddition? Right. Yes. Nucleophile, enolate, electrophile, beta carbon of enone.
At the beta position, aldehyde. That's what.
Wait, let me see. And this, I see two possible cuts here that we can make. Wait, I could say that this is the alpha carbon and this is the beta carbon of the enone right there, right? Or I could say this is the enone right here and this is the alpha carbon right there.
Yeah, I was thinking the cross probably
From the ketone here, this alpha carbon right here. Yeah, yeah. And to choose which one, right? Since there's multiple choices, we want to adhere to the C5 limit right there. So we could say that this is the nucleophilic alpha carbon and this is the electrophilic beta carbon right here. Because once we make that cut right there, we have 1, 2, 3, 4, 5 carbons that adheres to the C5 limit. We have a 1, 2, 3 carbons, that's even less. So that's good, right? Where once we make that cut right there, we know the beta carbon was the electrophile, which is going to be coming from the enone right here, right? Because this beta carbon, we said was the electrophile, and the electrophile for Michael is a beta carbon of an enone. So we had to put that double bond right there to make that into an enone, right? And then now this right here could just be left alone because this would just get deprotonated to become the nucleophile. We don't have to change anything there, but we do have to put an alkene right there because the electrophile for Michael is an enone, which since we said this is the electrophile, this has to become the beta carbon of the enone right there. So these are your starting materials that would create this here. The weirdest step for this whole thing is probably redrawing this. Yeah. Yeah. Was this the starting material that he put as well? Okay, that's good. The other one probably was this, right? Like where you make a cut here, and you say this was a star, this is a dot, and then you could say H, that, and then but there's a problem here, right? Why can't this be a starting material where this is the nucleophile and this is the electrophile? What's wrong with this? It's over the C5 carbon, right? Yeah, yeah. Also, the aldehyde doesn't usually attack the ketone, right? Huh? Oh, like the forward mechanism to go from here to here? Okay, let's do that. Right. So what is this overall reaction called? Where the first reaction was microaddition, the second reaction was aldol, intramolecular aldol. Robinson annulation, right? The first thing we did was Michael. The second thing we did was intramolecular aldol condensation, which overall is Robinson annulation. Okay, let's do the forward mechanism of this. Yeah. Yeah, the reagent we use is going to be something that can make this alpha carbon here nucleophilic, right? How can we make this carbon a negative charge? What do we have to use to make this carbon a negative charge? And base, right? Any strong base like NaOH, NaOCH3. H2O, if you use NaOH, if you use NaOCH3, then you use CH3OH, the solvent, the neutral version of that, right? Or if you use NaOCH2, CH2, CH3, then you use CH3, CH2, CH2OH. Mm-hmm. Yeah, that's the simplest case, right? Okay. Okay, let's go. Okay, forward. Okay, and this is gonna make this with NaOH, H2O. Yeah, so we have a strong base here. The strong base is gonna look for the most acidic hydrogen, which is gonna be the alpha hydrogen of this ketone here. That's gonna get deprotonated to form the enolate ion first, which is the nucleophile of the microaddition. Right. The nucleophile is not this O minus like we said earlier. The nucleophile is this alpha carbon right here, right? Because when we draw the resonance, the negative charge on this carbon is less stable, more reactive. The electrophile in this case, right, is not this carbon like we said earlier. The electrophile is this beta carbon right here, because we have a soft nucleophile. And enolate is considered a soft nucleophile, which would do a conjugate addition or 1,4 addition, right? When the nucleophile is an enolate and the electrophile is an enone, this is a micro addition. We're gonna reform that carbonyl, use this star alpha carbon to attack this dot beta carbon, shift this double bond over there, pop the double bond to oxygen to get this intermediate here. Right. And this star atom here is part of a ring, which is going to be part of this ring right here. And that's a carbonyl right there, because we reform that carbonyl right there. Right. Now, the next step is to protonate this alpha carbon using water, because water is our only proton source. We don't have H2SO4, we don't have H3O+, so we can't use that. Right. We're in basic conditions, where our most protonated state is the water here, right? Which is going to be a proton source. Reform that carbonyl, alpha carbon grabs the H, picks up the OH to get this 1,5 dicarbonyl. No, that's 1,3. Hold on. Okay, yep. 1,5 dicarbonyl. And then at micro addition, it's usually followed up with an intramolecular aldol condensation if it can form a stable ring, right? In this case, right here, we could say that we have 3 potential nucleophiles. This nucleophile, and this nucleophile here. We have 2 potential electrophiles. This electrophile here and this electrophile here. Now we're gonna choose which nucleophile and which electrophile would react with each other to make the most stable ring, right? So which one of these do you guys think is going to be the nucleophile here? Let's look at the star. A, B, or C? C, right. Now, which one of these would be the electrophile, A or B? A, right. Because we know that that's going to make a 1, 2, 3, 4, 5, 6-membered ring, the most stable ring we can make. So ignore the other alpha carbons and ignore that beta, that carbonyl carbon right there, right? So since we want this to be the nucleophile, what do we have to do with this carbon here? Right? How can we make this alpha carbon negatively charged? Deprotonate it, right? So we could use a strong base like OH minus to come in, deprotonate that, make the enolate ion here. Right? Where this is the nucleophile, this is the electrophile. Reform that carbonyl, star, attack the dot, pop that up there. This is an intramolecular reaction because the nucleophile is on the same molecule as the electrophile. In all intramolecular reactions, we always form a ring. And I like to number the attacking atom number 1. And then I go all the way into the atom being attacked, which is going to end up at number 6. Right? So I know we're going to make a 6-membered ring, right? But this is part of a ring itself. So that's why he probably drew that weird looking ring, bicyclic ring. Because, let's see, how can we do this? Let's see. Yes. Yeah, so we know that the nucleophile for aldol condensation is the alpha carbon, right? And the electrophile is the carbonyl carbon. So I first identified all of the alpha carbons. This is an alpha carbon, this is an alpha carbon, that's alpha carbon. Then I identified the possible carbonyl carbon electrophiles, which are those right there. Then I choose which one would give us the most stable ring. If I chose this as the nucleophile right here, and it attacks that, it's impossible. Can't make a 2-membered ring. If it attacks this, that would make a 1, 2, 3, 4-membered ring. That's too much ring strain, right? If we do the same as for here, 1, 2, 3, 4, too much ring strain, impossible. So these can't be the nucleophiles here. This has to be the nucleophile, but that can't be the electrophile because it can't make a 2-membered ring. So it has to be this one here to make a 1, 2, 3, 4, 5, 6-membered ring, which is stable and good, right? So that's the trick for intramolecular aldol condensation. Oh, if this was a ketone? Yeah, if this is a ketone, then this could be your nucleophile 1, 2, 3, 4, 5, 6. And it doesn't matter, it's a ketone because it's intramolecular. Or you could have done it 1, 2, 3, 4, 5, 6 here, right? Either way works, right? But the easier one to draw that you see is this one right here, right? Because you can make a six-membered ring from here, but he made it tricky by making a bicyclic ring, like a six-membered ring from this right here. So what we got to do is this right here. How the heck? Okay, I'm gonna do something really weird. I'm gonna draw it in like my own way, because like this, when you try to make a six-membered ring where part of the structure is a ring itself, you make a bicyclic ring, right? Where like there's two rings at once, so that's why it looks really weird. I'm gonna draw out the cyclopentane ring like this, and then the carbonyl is gonna be right here, right? Does this make sense so far?
Yeah.
Like how this carbonyl is the carbonyl, right? So that is gonna be 1, 2, 3. And then we want to make a new bond between 1 and 6, right? Because atom 1 is attacking atom 6. When that happens, we make a new bond between atom 1 and atom 6. That's the new bond right there, right? Because nucleophile attack electrophile. Let's do that. Star, dot. That's the new bond between the star and dot right there. Okay, let's combine this. 1, 2, 3. 5, 4, 4, 5. Does this make sense so far?
Yeah.
Right. It just looks weird because like, yeah, but that's a six-member ring right there. Where at carbon 6, it used to have a double bond O, but we popped that double bond O to make an O minus, right? Where the last step here is to protonate this O minus using water, our only proton source, to create that right there. This is going to be the exact same thing as that. It's just a different representation. Right.
Yeah, like that.
Friedel-Crafts mechanism, reaction, synthesis problem.
Yeah. Maybe like the mechanism of acylation.
Yeah, acylation, alkylation.
Not acylation like that.
Yeah, I guess he's not gonna say alkylation. He already says alkylation. Okay, let me look at the chat first, and then
So he's not gonna test on.
probably not because he already tested it. Yeah,
We probably talk about the organization.
yeah, for vocab. Right. And that was intramolecular aldol as well. Right. Micro and an intramolecular aldol, which is Robinson. Yeah, this could be given as a retrosynthesis question. This is most likely going to be a retrosynthesis question on the final.
The Benzene.
The
Oh, we're talking about
the thing we just did right here, yeah. Right. Please draw the forward synthesis. Yep, we did that. Okay. Alkylation and acylation. Yes to alkylation and acylation on the test, but alkylation is probably not going to be the mechanism. But it could be tested in some other way, like predicted products or vocab, like the limitations of it. And does it work on an activated ring or deactivated ring? Right? Which it will work on an activated ring. Friedel-Crafts reactions never work on deactivated rings. Yeah.
It's not changing.
Oh, so you wanted to go over Friedel-Crafts
Mechanism.
mechanism for acylation. Okay. And this is okay. Yeah, let's do that. Yeah. And then after that, we'll go over the synthesis problems with more carbon limits. But it's gonna be easier than this. But there's not, it's not gonna be intramolecular. It's gonna be like shorter. Okay. So Friedel-Crafts acylation. Some important notes. No reaction on deactivated rings. Where the rings, if they only have EWGs, no reaction. The only limitation for Friedel-Crafts, oh yeah, that was the only limitation. Right. Right. So let's say we have a benzene ring here. And we try to add this group here. Benzenes? Yeah, we could go over benzenes. Like, oh, shoot, sorry. Yeah. AlCl3. Right. This is a metal catalyst here that's required to do this Friedel-Crafts reaction go through. So first, let's predict the product. What do you guys think the product will look like from these reagents here? Yeah, right. Another way to think about it is substitute this chlorine with the whole benzene ring right there. Right. In this case, it doesn't matter because there's no EDGs on it. It won't direct any group anywhere. Right? It's an empty benzene ring. Right. Okay. So the first step of the mechanism is to make a good leaving group by having that chlorine attack the metal catalyst, AlCl3. That's the first step. Right. It's helpful to know the general mechanism of these EAS reactions, right? Where the benzene will first attack a good electrophile, and then that breaks the aromaticity, where there's a positive charge on the benzene ring, right? And then the last step is to restore the aromaticity by doing an elimination reaction, right? So right now, we're trying to create that good electrophile for the benzene ring, right? So here's the setup step before the EAS reaction. A halogen with 2 bonds, positive charge. Aluminum with 4 bonds, negative charge. This whole thing is a good leaving group. This good leaving group here will leave and form this ion here, right? And in mechanism, draw out the resonance structure of this ion here. This will be very important, right? Because since this carbon neocarbon here lost the bond, that will have a positive charge right there. The resonance structure that you have to draw is this right here. The pair of electrons on oxygen is going to go down and make a triple bond between that carbon neocarbon and oxygen to give you this type of structure here with a positive charge on the oxygen, right? And there's a specific name for this ion here. Do you guys know the name for this ion? Oxonium is OH2 plus, right? Enolate is the alkene O minus. There's a name for this ion here. Acylation ion, right? That's important for this mechanism. Yeah, draw the resonance structure of this one here in the mechanism, because they could take points off because necessarily like wanted you to draw the mechanism for this as well. Pascal might want you to draw the mechanism for the resonance for this one as well. Right? So you could use either this form or this form. That's the electrophile for the benzene ring, right? So let's draw in that benzene ring here. I'm gonna use this form here because that's the more major form, the more stable form, where I'm gonna say that this is my nucleophile, this is my electrophile. Nucleophile attack electrophile, and then we're gonna shift this bond onto that oxygen right there, right? This is the addition step here. When we do that, we get this new bond between the star and the dot bond right there. Positive charge here, there. Dot is attached to double bond O because we pop that triple bond to the O, and it's used to right there, right? Now we broke the aromatic ring here to restore the aromaticity, deprotonate this alpha hydrogen right there with this base right here. Right, the good leaving group that left. this chlorine is now neutral because it only has one bond. The aluminum still has a negative charge because it has 4 bonds. Right? Think of this as a negative charge chlorine that's going to attack the H and remake that double bond right there, which will restore the aromatic benzene ring. And then reforms of these are side products, which you will not have to put on the predicted product, probably mechanism, but not predicted product or synthesis, HCl and the AlCl3 catalyst. It gets reformed. Right? But for predicted product, this is the important thing here. The acylated benzene ring. So that's the mechanism for that. Let's do synthesis after this. Oh yeah, yeah, I forgot about that. Yeah, I'll go over Wittig reaction after this synthesis problem here, and then we'll go over shoot. Yeah, know the mechanism for nitration, sulfonation, bromination, halogenation as well. That could be a mechanism question. All those EAS reactions. Like not just acylation. Where the first step is to set up the electrophile, and the second step is addition, and then third step is elimination to restore the aromaticity. Okay. Yeah. Oh, right. For Friedel-Crafts acylation, that's good, right? The first step is this acyl group with the AlCl3. Second step, H3O plus step. But Pascal didn't go over that last part for the mechanism.
Think of like how it attaches.
Yeah, this would attack the loose acid. Does he cover that?
I think you mentioned.
Oh, he mentioned it.
I
Okay.
think you showed the mechanism. Like,
Yeah, right. The reason why we need acid workup is because this loose acid here is still open for this oxygen to attack, and that would form the oxygen aluminum ion, which we don't want. But then to get that clean acyl group on the benzene ring, we just work it up with acid workup, which will cleave that group. Right. It's a very short mechanism. Let's just go over it really quick. This aluminum here will get attacked by that oxygen to get this structure here. Right. Friedel-Crafts acylation requires an acid workup step. Friedel-Crafts alkylation does not require acid workup step. Right. When the oxygen attacks the aluminum, we have this Al and Cl3. Oxygen has a positive charge, aluminum has a negative charge. And the last step here, don't need to worry about the mechanism. H plus will just go back to the clean acyl group. And then the A, well, actually these will not become AlCl3 again. It's just going to become Cl minus Al3 plus ions. Right? Yeah.
You suggest that we do like H3O plus or H plus. If it does come up.
The mechanism, it's more accurate to do it this way. Right? Yeah. So I recommend whenever you get this acyl group here, the carbonyl oxygen attacks the AlCl3 Lewis acid again to create this ion with the oxygen positive charge and the aluminum negative charge. And an acid workup would just cleave that off to create the clean acyl group, and then the chloride minus ion, and then the Al2 plus ion. Right? Yeah.
Somebody wanted to do Wittig.
Yeah. Okay. Let's do that Wittig reaction. Yeah. Okay. Okay. Wittig reaction. So here are the 2 important notes that you need to know for this reaction. Carbonyl plus, Pascal calls it unstabilized. Unstabilized. Or you could say unconjugated. ylid will give you a Z alkene. You'll get an E alkene if you have a stabilized or conjugated conjugated ylid. Right? It doesn't matter if the carbonyl is conjugated or not. What matters is the ylid, right? The carbonyl will not affect the E or Z. The ylid will affect the E or Z alkene. Right? So let's do the Z alkene. Let's say we have this carbonyl reacting with this ylid right here, right? To predict the product quickly without doing the whole mechanism, you first identify your carbonyl carbon, which is this carbonyl carbon right here. And then you identify your ylid carbon, which is this carbon right here. And then there's always going to be a double bond between the carbonyl carbon and the ylid carbon. So let's draw that double bond out right here. Right. Let's say this is the blue carbon that I labeled. And this is the double bond between the blue and green carbon right here. Right. And let me make the ylid have something else so that we can look at the Z and E product, right? Is this an unconjugated or conjugated ylid? Unconjugated, right? Because this double bond here cannot do resonance with anything here. So if it's an unconjugated ylid, we want to create the Z alkene, right? Where to figure that out, make an invisible line through the double bond right here. And I look at one carbon at a time. If we look at this carbon here, this isopropyl group has a higher priority than that methyl group. So that's the higher priority group there. Let's look at this group here, right? This group is going to be higher priority group than the other side because it has that methyl group right there. So if that's the highest priority group and we want a Z alkene, we want that group to be on the left side, the same side as the high priority group on the other side, right? Where the green carbon is part of a 5-membered ring, or not 5-membered ring. Oh my God.
It's hard to
I didn't need that methyl group there, right? Because there's a hydrogen right there. Right, so let's just keep it as it is, right? Because we're comparing that cyclopentyl group with a hydrogen right here, right? I thought that was part of a ring, but that's not part of the ring. So the highest priority group here is that cyclopentyl group right there, right? Which we're just gonna put that cyclopentyl group right here. Now the highest priority groups are on the same side. This is the same side, Z. Hydrogen, we can leave as invisible right there. Right. Now let's say we have something like this here. Okay, so do the same first step, identify the carbonyl carbon and ylid carbon. This is the ylid carbon here, not this, because that's a carbonyl carbon. We make a double bond between those two carbons. Right. You can also think of it like this. Whenever we make that double bond right there, this carbonyl gets eliminated. This phosphorus triphenyl gets eliminated as well. Right. And then we just make that double bond between the blue and green carbon. Yeah, it's just these two reacting with each other, no other reagents. And ylid will automatically react with the carbonyl. Right? And I'll go over the mechanism of that as well. Yeah. Mm-hmm. No, there's something going on here. Okay. So we have that. This is the blue carbon, double bond between the blue and green carbon. It's a high priority group for the blue carbon is this group right here, which is this group right here. Is this a conjugated or unconjugated ylide here? Conjugated, right? Because this double bond can do resonance with the ylide. If it's conjugated, we want the E alkene, right? So let's make that invisible line through that double bond. Highest priority group on that carbon is this one here. Where do we want to put this group here? On the left or right side? On the right side, because we want this to be the E alkene. So that's going to be the carbonyl there with the group right there. That's the E alkene. So that's the difference between them. Right. Okay, let's go over the mechanism of this. Okay. And I will also show you guys how to make the ylide from a haloalkane. Wait, let's go over that first, actually. So let's say we have this random haloalkane right here. We can make this into an ylide where this carbon will have a double bond with phosphorus triphenyl here. To do that, the first step is to introduce that phosphorus triphenyl as a nucleophile, which we do an SN2 reaction. This phosphorus here will attack that electrophilic carbon and kick out that leaving group for SN2 reaction. 118A. When we do that, this phosphorus here would have a positive charge. Right. The next step here is to use some kind of strong base like NaH or N-butyllithium. Both would work to deprotonate the most acidic hydrogen, which is this alpha hydrogen right here next to the phosphorus. Right. The H minus will grab that alpha hydrogen and make that double bond right there to create the ylide and neutralize that phosphorus at the same time. Right. Now this is the ylide right here. Right. When we look at the resonance structure of this ylide, we will see that there is a negative charge on the alpha carbon and a positive charge on the phosphorus. Right. So whenever you see the ylide, think of that ylide as the nucleophile. This carbon here is the nucleophile atom for this mechanism. Right. So let's just introduce some kind of carbonyl like this cyclopentanone here. Right. And let's get that ylide that we just formed at the first step here. First, identify your nucleophile, which is this ylide carbon here, and then the electrophilic carbon, which is that carbonyl carbon right there. This nucleophilic carbon here will attack that electrophilic carbon and then pop that double bond into oxygen right there. Right. And then here's the trick on what I like to do for the mechanism. For this mechanism here, there's going to be a box-looking structure, right? Where let's draw in that new bond between the star and the dot, right? This star is that star, this dot is that dot. So this is the new bond between the star and dot right there, right? Draw the box like this, where the star has a phosphorus triphenyl, where the phosphorus has a positive charge. The dot used to have a double bond O, but we pop that up to become a single bond O minus, right? And then everything else is just attached to the star and dot. The star here is attached to the isopropyl group. Let me make this. Let me make this easy so we can see the Z alkene here. Right. Okay, so that's the dot right there, which is attached to an ethyl group and methyl group right there. Ethyl group, methyl group right there. Right. Think about the oxygen and phosphorus bond as very strong. Like they're very attracted to each other. The O minus is going to attack the phosphorus plus to create this box in the mechanism. New bond between oxygen and phosphorus. Right? Now that's the box structure right there. And think about the last concept I said. Oxygen and phosphorus makes very strong bonds with each other. They want to leave from that molecule right there, right? So they can make a double bond from these electrocyclic arrows here. This bond is just going to go there to make a double bond, and that bond is going to break and make a double bond right there, right? This will just leave as a side product, making that alkene right there, which will give us this final product here. Right. You don't have to put this as a product for your predicted product. The important thing here is this alkene right here. Right, which is organic. This is not organic.
What's the thing with conjugation again? Is it the unconjugated?
Right, for illid, right? The carbonyls doesn't affect the thing. Yeah, right. Let me give you practice problems on that based on those concepts. Yeah. Yeah, yeah.
I think technically this says that it doesn't require 17 and 18, but technically don't you need to put a protecting group after you do so I'm doing an isomerization. I want to make this double bond here
Right.
to do the alcohol dehydration. But can't this also protonate this?
Oh, it can protonate that.
Yeah, even though it's an aldehyde.
Yeah, the carbonyl oxygen will still get
So
protonated.
you technically
Are you trying to isomerize
or I wasn't sorry, I was trying to do isomerization, but I had to do alcohol dehydration.
alcohol
So
dehydration?
getting it here. But
Right.
technically
You
I
have to
protect that.
right. You do right
Yeah.
because if you protonate that, it's intramolecular reaction
I
gonna
noticed
happen.
like this Leavens worksheet, it's like a bunch of it's just missed a lot of like different protecting.
Protecting groups, yeah. That's good. That's good. Yeah. Okay.
I got 100 on both. First person to get extra.
Okay. Okay. Try these 3 Wittig reaction practice problems. Let's explain how the alkene forms again from the ring. Alkene forms from the ring. Yeah, so for the Wittig reaction, the alkene forms from the ring from this electrocyclic arrow here. Right, we want an alkene right there between the star and dot bond. These are the arrows to make that bond right there. Right, where this will leave as a phosphine. And this would make that double bond right there between the 2 R groups. But you don't have to draw out the whole mechanism to predict the product. You could just identify the carbonyl carbon and ylid carbon and make that double bond between them. And it would be a Z double bond if your ylid is conjugated and stabilized. It would be, wait, did I say Z? It would be a Z alkene if your ylid is unstabilized and unconjugated. It would be an E double bond if your ylid is conjugated and stabilized. How was the, okay, will Robertson reactions sometimes have no heat as reagents? So Mescal, he does not require heat. He just assumes it goes all the way through. So you won't need heat for Pascal's class. Right. Nice shirt. Thank you. Yeah. Uh-huh.
For this one, it's for one of the leavances.
Uh-huh.
I don't need a protecting group here, right? Because I'm just reacting with NaOCH3. Or would NaOCH3 react with carbonyl? Because I feel like now that they introduce groups, it's like paranoid.
Oh, it's paranoid of you, yeah.
Yeah.
Like you gotta watch out for every single thing, right? When you try to do NaOCH3,
Like pretend there was like I just
and then are you trying to make a double bond right there?
yeah.
Between that, right? You would have to use a protecting group because the alpha hydrogens here are acidic, right? Because you have it from the enolate ion,
Yeah.
right? So it could react with the thing and make an enolate ion instead of making a double bond there.
Okay. So
Right.
it was a good thing that I added.
Yeah, it's a good thing that you added that
Okay.
protecting group,
And
right?
then stock off, right? If I just like add an extra steps, like adding it and removing.
Yeah, they won't. That's actually how it's done in lab. So that's actually the more accurate way. Like when you TA sees that, they'll be like, oh yeah, that's normal. Right. So they won't take points off for that. Yeah.
Thank you.
Uh-huh. No problem. Mhm.
Good luck, guys.
Mhm.
See ya.
See you, Arnav.
Got this.
Okay. 3 volunteers to come up and try these problems. Yeah. Okay. Yeah. Uh-huh.
I haven't even done it, but I'll do it.
Yeah, that's good. Right. We got to be careful here because this is the carbonyl carbon and that's the elliptic carbon right there. So the double one is going to be between that carbon
Oh,
and
so
that
wait,
elliptic right
that's
there.
gonna be make it trans.
Oh wait, that is double bond. Right, that's good. Never mind.
It's gonna make it trans, right?
Yes, it will make it trans, and this is trans,
Okay.
right? Because it will make the lines through here. The 2 high spectral groups are on the
Yeah.
opposite side.
That's right.
Yeah, that's right. Yeah, nice. Because this is a stabilized conjugated elliptic, which will give the E alkene, right? Where the alkene is going to be between this carbonyl carbon and that elliptic carbon right there. Right, that's the double bond between them. Right. Yeah. Do you guys want to try the next ones? Oh, okay, number 1. I see. Yeah, that is right.
Okay.
We want the E alkene, right?
Is this one?
This one right here on this one. Let's see. Which was going up?
Yeah, like I just put them both up.
Oh, right. So you have to choose one, the highest party group, to be
Oh.
up, right? Because
So
if
in
you
this
make a line
case,
through
it's
there,
a-
yeah, it's a method that goes down, right? The highest party group goes up. On the opposite side, the method
Looks
group
better
goes
that
down.
way.
Yeah, right. Yeah. Try. Uh-huh. Yeah. Let's see. C3C2, and then that's OH, and that's alcohol aldehyde, and then this is Z. So this is that's right. You want to draw that on the board after her?
Okay.
Yeah. So she's the second one. I see. Try the third one. Yeah. Yeah.
This is a big responsibility.
So, 0.5.
Unconjugated, right? So it's
Yeah. Oh, this is a tricky one here.
There's a chance that this is conjugated.
Right. This is conjugated, right? But is this the carbonyl or ylid? Right. This is
Oh, you
carbonyl.
need a conjugated ylid.
You need a conjugated
Okay.
ylid. Right. This is the tricky one here. This is the trickiest question. Right. So yeah, since the ylid is not conjugated, it would become a Z alkene, right? It doesn't matter if the carbonyl is conjugated. Yes, like that, right? The carbonyl doesn't matter if it's conjugated or not. It's the ylid that matters, right? This is the trickiest one.
I don't think anybody else is gonna join in.
Okay. Yeah. Thank you for approving that. How many people like try to like join?
Oh, there was a fun.
Oh.
I don't know.
Oh my
Like,
god.
some-
Yeah. Thank you. Okay. Let's see. Okay. Right. So for the second one here, we have a haloalkane, which is not an ylid, not a carbonyl. But we see in the first reaction here, we are trying to make an ylid with the phosphorus triphenyl, which would create this intermediate first, right? When the phosphorus attacks the carbon and kick out the bromine, we're gonna get this intermediate right here with the positive charge on the phosphorus, right? But then the NaH, the strong base, will just make it into the ylid right there, right? And we know this ylid is unconjugated, making the Z alkene between the carbonyl carbon and the ylid carbon. For the third example here, this is the trickiest one. Some people think this is conjugated and they make the E alkene, right? But the carbonyl does not affect the E or Z alkene. It's the ylid. It has to be the ylid one, right? That's a common mistake that people make. They see conjugation here, they automatically think E, right? But it's not the ylid that's conjugated. Yeah. This could be a good exam question here to try to trick you, right? How do we tell if the carbonyl is conjugated? So you can tell the carbonyl is conjugated if it is right next to an sp2 atom that can do resonance, right? We can move this double bond down and do resonance with the whole benzene ring here. It does have to be a benzene ring. It could be a whole row of alkenes doing conjugation, right? How can we tell Wittig has happened if it's synthesis and there's no carbonyl in the starting material? Yeah, so there was multiple ways to do that. If you see an alkene in the product, right, a Z or E1, you could say that comes from a Wittig reaction, or you could reaction, right? Where if you see a Z alkene, what reagent do you use to reduce an alkyne into a Z alkene, a cis alkene? What reducing agent do you use? Poison catalyst. What poison catalyst do you want to use? H2 Lindlar's catalyst, right? But if you wanted to make a trans alkene from an alkyne, what kind of reducing agent do you want to use? Na radical, 2 equivalent ammonia liquid, dissolving metal reduction, right? If you want to make an alkane from an alkyne, like go all the way through to the alkane, what's H2PDC? That's the overreactive one that would go all the way down to an alkane, right? You could do the alkyne route or you could do the Wittig route, whichever is easier on the synthesis. But if it works, then it works. Then you get full credit for that. Yeah.
He won't discount if you do it more or he won't take away points if you do the longer route.
Some professors don't like that you do it longer route and they take points off, but some professors do allow that, like that longer route.
From like when he goes over the exams during lecture,
Yeah.
the past couple times, I think he's been a little
Oh, linear? Yeah. He's like, this one would work too, this one would work too, and stuff like that.
and he says it's like he gives the TAs like guidelines. He says
It's fine. Yeah.
And they'll probably
Yeah. So yeah, if you use the longer route, don't worry. If it works, then you get full credit. But make sure like it's high yield, because like if it does work and it's low yield and like there's some other mixed products, then that's more iffy. They could take points off for that. Could you draw the final product for 3 a little bigger? Okay, yeah. Let me draw the final product for 3 a little bigger. Right. where this is specifically a Z alkene because this is an unconjugated ylid. Pascal calls it unstabilized. So you might see that in vocab. If you see unstabilized, think of unconjugated. If you see stabilized, think of that as conjugated. Right? The carbonyl here does not affect the EOZ. The carbonyl, yeah, does not affect the EOZ thing.
I don't know.
Okay. Synthesis bonds with benzenes. Yeah, let's go.
After the Benzene, if there's time, can you just do some synthesis problems that are like that cover a little bit?
Yeah, yeah. I'll do synthesis for benzene, midterm 1, and the new material. Yeah. Okay. So okay, let's try the synthesis round here really quick. And while you guys work on that, I'll think of other synthesis rounds for the new material first and then old material. Right. So what directing group is that group right there? This is EDG or EWG. What is the partial charge of this first atom directly attached to the benzene ring? Partial positive. Partial positive is an EWG. Right. So meta director, right. Right, right.
But can you use like that exposure? But that's not gonna change the thing. Let's just say
Oh, you think of using that would be still partial positive because it's attached to the oxygen. Right.
Would it be this? SO3. I didn't draw it out, but like SO3 would pop over here. H2 makes this
Ah, so here's the confusing thing. Is this an EDG or EWG? EWG, so that's a meta director. Wait,
okay, so then reverse these steps.
yeah, yeah, reverse those
And then
steps.
that's it.
And then SO3 and then that thing and then deprotect to the
then-
SO3.
Okay.
Yeah, and then Jones and then H2SO4 water and heat to get rid
Yeah.
of the protecting group. Yeah, you got it.
Yeah, I tried doing it all in my head.
Oh, yeah, on your head? Yeah, yeah. Since this is your favorite, right? Your favorite section? Yeah. Yeah, no problem.
Very good. Get rid of
Yep. How can we get rid of this benzylic carbonyl? Right, because Wolff-Kushner? You can do Wolff-Kushner as well. That's option. Right? Yeah, it clears the carbonyl. Right. Wolff-Kushner can cleave the thing in high yield, the carbonyl in high yield. Right.
It can also reduce it, or like no, H2 also activates it, right?
Yeah, HCBDC. That's the best route because Wolff-Kushner, you need a lot of heat, a lot of heat and base. That's extreme conditions, right? To get to the high yield, right? If you don't have a lot of heat and base, then that's low yield.
So if you want to just do H2PDC and leave it off.
Yeah, HCBDC is leave it off, right? But let me just say like the whole thought process of the synthesis problem before going over the reactions, right? We see that this new group that we attached here is ortho to that group right there, right? But this group is not an EDG, it's an EWG because the first atom attached to that ring is partial positive, which EWGs are meta directors, right? So we gotta convert this to ortho paradirector first to add that group ortho to it. To convert it to ortho paradirector, we gotta get rid of that carbonyl using H2PDC, right? Now, once we reduce that, carbonyl to make that into an EDG, it's now an orthoparadioactive there. When we try to do Friedel-Crafts, I just realized something. But I think it will still work. I will still work. I think it will still work, right? If Friedel-Crafts acylation, which would do ortho and para, right? But we don't want the para position because there's nothing in the para position here. Protect it with SO3, H2SO4. I was confused about this question like some time ago, but I think I know the reason why now, right? You notice how SO3H is a deactivator,
Yeah.
EWG? Because we have an activator here, Friedel-Crafts reaction can still happen, right? It will not happen if it's just EWGs on the ring.
If it starts with like
Yeah, right. If there's an EDG there, then it will activate it enough to allow for Friedel-Crafts reaction to happen.
they're still better
Then
strong.
EWG, right? So if there's an EDG on the ring, then Friedel-Crafts reaction can still happen even though there are EWGs on the ring, right? But if that wasn't there and you try to do Friedel-Crafts, no reaction, right? So the next thing here is to predict the reagent for Friedel-Crafts, which what I like to do is I just ignore that whole benzene ring and put a chlorine right there, and then copy and paste everything else like that, which is this group right here with the AlCO3. And what did we say Friedel-Crafts reaction always comes with afterwards? Yeah, second step H2O plus. Right. And that would get to this acylated benzene ring here with the SO3H group on it still. Now, what are the last two steps here? Yeah, H2SO4, water, and heat.
And yeah.
Oh, there's actually another step here. I just realized that. I didn't see that. Oh my god.
We also have to bring back.
Oh, actually, no. Is this one last step? Never mind. Yeah, using Jones. Right, bring back the carbonyl at that position, Jones. You might see a CrO3 H2SO4 water on practice exams. Right. When you see chromium and oxygens, that's Jones, which would oxidize that benzylic carbon back to the carbonyl there.
It's just like Jones, right?
Yeah.
And then he.
Yeah. He probably won't. Yeah. SO3H is a strong EWG, but oh right. But this is an EDG right here, right? EDG takes priority over any EWG, which in EDG is an orthoparadioactive. So in this case, it tends to work out because ortho to that is that EDG right there, meta to that is that Vic there. So it will like work out at the same time. Yeah. Just benzylic, not allylic. Right. What would oxidize a allylic? Oh no, not carbon. Allylic alcohol. Like, what if we wanted MnO2? Right. That's the thing. Right. OH. MnO2 will oxidize benzylic or allylic alcohols into carbonyls like that. Right. Where what did we just form here? Once we oxidize the allylic alcohol. Right, what is this functional group here? The alkene next to the carbonyl, enone, right? And then from this enone, you could do a whole bunch of reactions with soft hard nucleophiles. You could do micro addition and then Robinson addition. Yeah, ignore this alcohol here because that alcohol is not allylic or benzylic.
Yeah, I know.
It's too far away. It only does allylic or benzylic alcohols, right? Yeah. So if it's a benzylic carbon here, then that benzylic carbon would oxidize to the carbonyl there. Right. Yeah. No alcohol, but it's benzylic. Right. Does it work if it is allylic? No, it has to be benzylic. Yeah, no. SO3H is an EWG, but because there is an R group here, which is an EDG, Friedel-Crafts reaction can happen. If that EDG R group was not there and it's just the EWG SO3H, no Friedel-Crafts reaction will happen at all, no reaction. But because there is an EDG there, a Friedel-Crafts reaction will happen. Can you use PCC instead of Jones as a reagent? PCC as Jones. Well, not for this example, because you need Jones to work with that. You can't use PCC. PCC is a weak oxidizing agent. Jones is a strong oxidizing agent, and we need a strong oxidizing agent to oxidize a benzylic carbon to a carbonyl. So you don't use PCC. Oh no, actually for PCC, right? For this one here, right. If you just do PCC, nothing will happen. Yeah, nothing will happen. Right. PCC and Jones will do something different for primary alcohols, right? Like if you react the primary alcohol with PCC, what would you get? Aldehyde, right? And if you react that primary alcohol with Jones, carboxylic acid, right. Can you write the last step a little bigger? Last step, right? This last step here is Jones, right?
Bring the whiteboard closer.
Yeah, no problem, Amar. See. Oh, I see. Oh no, it's locked. It's locked. I can bring my Mac closer. Okay, is this better? Okay, I think that should be fine. So we can sort of summon a carbonyl at the benzylic carbon with Jones, H2SO4, and water. Yes, you can summon that carbonyl at the benzylic carbon with Jones, acid, and water. Aside from how PCC and Jones react with primary alcohols, could you use Jones in place of PCC? You can't use PCC in this reaction here. PCC is not strong enough to oxidize or summon carbonyl to the benzylic carbon. You have to use Jones, not PCC. Oh, in other reactions. Well,
It depends on
it depends on the reactant. Yeah, right. It depends if it's a primary alcohol, secondary alcohol, tertiary alcohol, nothing happens. Primary alcohol with PCC creates an aldehyde. Primary alcohol with Jones creates a carboxylic acid. Secondary alcohol with PCC or Jones, it does not matter. Always creates a ketone from a secondary alcohol. Right. And yeah, 118C, you'll learn about benzylic carbons and other things as well. But don't worry about that here. Yeah, you could just write Jones. You don't have to write CrO3. Yeah.
Where does the oxygen come from when you react with Jones?
The oxygen will come from, I think, the oxygen from chromium, but I did not learn the mechanism, so I don't know like how the whole mechanism works. I don't think you need to worry about that mechanism. Yeah. At the benzylic carbon. It can't be on the random carbon. It can't be something like this. But like you try to do that, do Jones. Like it won't do this. No. Right. Yeah. Because this carbon here is not benzylic. Yeah, don't do that. Yeah, this is no reaction. Yeah. Right. Okay. Okay. More synthesis sums on this new material or old material?
Um, let's do old and then go back.
Old and then to new, or let's actually start with new first and then go down to old, because like when you review old material, it's like quicker to pick up, right?
Okay.
The new material is like harder to pick up because you just learned it. Yeah, right. And I think someone asked about the new material synthesis earlier. Old. Oh yeah, old. Yeah, we were asking old. Okay. Oh wait, old. Okay, I'll give you guys two, old and new. Old and new synthesis. Let's see. The first one's gonna be old. The second one's gonna be new. Let's do some kind of. Okay. Hmm. Okay. Let's see. So the first synthesis is going to be 3 reactions long. The second synthesis is going to be 2 reactions long, right? Mescal, similar synthesis. You guys see this clearly? Yes. Okay. Huh? No, I'm gonna eat after. I'm gonna eat the In and Out. Yeah, and then I'm gonna head back. Yeah, I got my In and Out bag. Yeah, yeah. Thanks for the In and Out. Oh yeah, let me pay you guys. Let me pay you guys back for the In and Out. Are you sure? All right, thank you. Yeah, thank you. Yeah. On the left side,
Yeah.
on the one, yeah. And based on heat, that would add a bromine on not the vanillic position, but the allylic position, right?
Only a little.
Yeah. So BR would add the bromine at the allylic position, right? But if we wanted the bromine at the anti-mark countercalc side, there is a reaction that we could do that with. Right, I'll give you a hint. What sound does the lion make?
Oh my God, I hate that. That's so I can never ever remember like
Roar,
yeah.
roar. Yeah, roar with not BR2 because we don't have 2 BRs. We only have 1 BR and 1 H. Because HBR. HBR and roar. Right? Where H would be on the more subside, BR would be on the less subside. Right? Anti-mark, which will only add 1 bromine to the less subside here. Right? Now, where do you think this come from? Let's go backwards. Let's go retrosynthesis, because you get points back for going backwards as well. Right? What is this relationship between these 2 alcohols here? Are they syn or anti? Syn addition. What reaction makes a syn addition? Hydroversion is anti-mark, adds only 1 alcohol, but we have 2 alcohols here. Osmonium. Hg is the oxymercuration demercuration. That only adds 1 alcohol on the mark side, the oxymercuration demercuration, the Hg one. The hydroversion oxidation with the boron creates only 1 alcohol as well on the anti-mark side. But we want 2 alcohols on the alkene, right? Syn addition, which is the osmonium one, right? OS, O4, second step, Me2S, I don't know. Right, now how can we create a less stable alkene here? LDA, right? Or tert butoxide, bulky base, right? Because we want the Hoffman alkene, right? So yeah, you can do the second one. Here you go. You can do LDA or tetroxide. Any bulky base, right? Any bulky base. Is that the reagent for osmium? I'm not too sure of the second step. Oh, H2O?
Am I wrong?
There's,
OSO4
I have
H2O.
it. There's multiple ones.
Oh,
There's,
could I use that then?
I think so. I
Alright.
think it, like, unless I'm mixing it up.
I think
you can use
osmium
H2S.
with, like,
H2S. Yeah, H2S is a reducing agent.
No, that's ozonol.
Oh, that's ozonosis. Oh, I think I was thinking about the O3 one with the Me2S and O3. Oh, it's NaHSO3. Okay. Let me change that up. Yeah. Second step for osmium tetroxide is not Me2S. It is NaHSO3. There's multiple ones. Like I've seen multiple second steps. It could be H2O, something like that as well. I'm not too sure on the second step. Yeah. PCC, oxidize that, and then from here, what is this here?
Oh, it's like an RX.
RX, haloalkane, right? Which is an electrophile or nucleophile? It's an electrophile, right? Because this carbon here is partially positive, which is because that electronegative atom there is pulling its electrons like that, making that right there. No, we can't. Right, we do want to do 1,4 addition with this R group right here, right? But what weak organometallic? Yeah, organocuprate.
Would this add?
Oh, this would not do anything with this because this is an electrophile. This is an electrophile. Electrophiles do not react with each other. Yeah, two of the ethyl groups right there with the copper lithium.
So if you had another one right here coming out, then that's when you want to add that as well. Or when would you want to?
Oh, right. Yeah. Right. If you want another one right here, right? Like let's say we wanted this ethyl group right here. Then the second step would not be acid, right? Because the second step acid would protonate that alpha carbon. But if we don't want the alpha carbon right there, if we want that thing, then we use this thing right there that you use, right? Which would attack that carbon and kick out the bromine there, right?
Wait, so the copper lithium, it reacts directly with the alkene.
Right, because what is this functional group right here? An alkene next to an ketone. What is that functional group called? Enone, right? Enone, and we see the new group on that beta carbon right there, right? Which is why we want to use a soft nucleophile, organocuprate. Soft nucleophile. We don't want a hard nucleophile. We don't want MGBR. We don't want Li. Because if you use MGBR or Li, it would attack this carbonyl-carbon instead. Yeah. We don't, because this enone here, right, would just attack the beta carbon, right? And organocupric R2COLI would just attack the beta carbon. It won't attack the carbonyl carbon, right? It's because this is a soft nucleophile, which will attack a strong electrophile. Carbonyl carbon and pop that to the OH.
Over here. Then you would need a.
Oh, over here?
Yeah, like say if we use instead like MGBR.
Oh, so
would you need to do a protecting?
Oh, if you wanted an R group here and not here?
Yeah.
Let's see. What? And nothing here, right? Nothing there. Yeah. So that I think it is possible, but I don't think it will use this kind of like reaction here with the soft and hard nucleophile, right? Because whenever we have an enone, we can only attack two places. We can either attack the beta carbon or the carbonyl carbon. Those are the only two spots we can attack, right? There's no hydrogen here. Yeah, there's no hydrogen on that carbon. Yeah, that's because I have the methyl group right there. Right. If I don't have the methyl group here, then there would be hydrogen there. But yeah. Right. I think if I like think about it, like I could think of other reactions that could do that happen, but not what I want to test here. Not the new material. Right. H3O plus here would make this into a hydrogen, which I gave originally, right? If I give that as the second step, right? So this is the difference between alpha protonation and alpha alkylation, right? Because when we do the whole mechanism here, this carbon here of the organocuprate is going to attack that beta carbon of the enone, shift the double bond here, and pop the double bond into oxygen, right? And that's going to give us this structure here. O minus that. And that's the methyl group right there.
Somebody was asking in the chat.
Uh-huh.
There isn't.
Well, the original synthesis product I gave you guys, there is an acid breakup, right? Because at that alpha carbon there was no R group there. If there was no R group there and that's hydrogen, then the second step would be acid breakup. But since the new synthesis problem here has that R group, then the second step would not be acid breakup. The second step would be the haloalkane right there, right? And the reason why is because once we added this new R group already, right? This is our enolate ion here, where the alpha carbon is the nucleophile or base. And then if we do the acid workup, right, then that alpha carbon there is gonna get protonated, where there's nothing here, just a hydrogen. This could be a nucleophile. If we introduced a haloalkane here, this alpha carbon here would attack that carbon and kick out the bromine there to get this new alkyl group there, right? So this synthesis could be harder if there was a new R group there, right? If that R group wasn't there, then you do acid workup, H2O plus. Where the acid would be that H right there on the alpha carbon, right? Because it's gonna come back down. In this case, it attacks the haloalkane, kick out the Br to get that new R group right there, right? But if we have this as the product, then some acid will work up. H2SO4, H2 plus doesn't matter. Go back down. Alpha carbon gets protonated, right? To get to this point here, where the proton is going to be that proton right there, which you can leave as invisible, right? So once you get the enolate, you could either protonate it, the alpha carbon, or you could either alkylate it, the alpha carbon. Right. Uh-huh. If I change the order, like change the order of the reactions, or
Yeah, I guess. Yeah, it says what happens if you switch the order of the steps for the second synthesis when it's still working. Like I guess like from the Cooper.
oh, like this right here? No, it would not work, right? Because when we have, I'm gonna erase this top part here. Right. Yeah. Right. When we have an enone and we react it with this haloalkane and then the second step organocuprate. The first reaction here reacted is an electrophile. This is also an electrophile. Whenever we see an enone, there are two electrophilic carbons, this one or this one here. Yeah, right? Electrophile would not react with electrophiles. No reaction, right? Electrophiles don't react with each other. Electrophiles would react with the nucleophile though, right? But if you had a strong base, right, like NaOH, NaOCH3, which one would be your most acidic hydrogen? We went over this earlier. Would it be A or B? A, right. This one would be the most acidic hydrogen because when we deprotonate it, it gives us the most stable conjugate base, right? So if there's a base there, then that's the reaction that would happen right there, where this alpha carbon here would get protonated. Would be the nucleophile, right?
I guess they were saying if you did PCC first and then the.
Oh, if we did PCC first here.
And then the.
Oh, and then the organocuprate. Yeah, that's the.
Oh, wait, my bad. So I guess there's the.
Right. If we try to do cuprate first and then PCC, that would be no reaction as well, right? Because there's no electrophile here at this point.
Yeah.
Right. This is a nucleophile. This whole alkene is a nucleophile, which could attack an HX, X2.
So if you did like
if we did, yeah, it would make an enone. Yeah. Which is this part here.
Yeah.
Right. Yeah, right. Right. When we did PCC, we converted a whole nucleophilic molecule into an electrophilic molecule, enone. Yeah. The most acidic hydrogen is the hydrogen A on the left side, because when we deprotonate this, the conjugate base is more stable than this side here, we can do more resonance. Oh, what was the question? Sorry. Yeah, this is extra carbon right here. The carbon next to the alkene. Alpha, beta, gamma. Yeah, that's the gamma carbon, right? Gamma carbon of the enone is more acidic than the alpha carbon of the enone. Wait, that's the gamma symbol, right? I think. Okay, okay, this is alpha.
So like, like how I mentioned earlier,
Yeah. Let me erase this spot. I don't know. Maybe try it here.
yeah.
Yeah.
So,
Oh, okay, it's 10. Yeah, last question.
yeah. Okay. Right. Like if that's what makes it more acidic versus going trails right here only.
Yeah. Right.
Oh.
There's a longer tail here, more delocalized, shorter tail here, less delocalized. Right. More stable conjugate base, more acidic acid. Okay. Any last minute questions? There was a mechanism he did from this lecture that involves an alkyne. It was like alternatives to using amines. So alkyne can be used as a nucleophile if you deprotonate the terminal alkyne hydrogen to make the alkyne anion. And that could act as a Grignard reagent, which can do 5 different reactions. It could do SN2, it could attack an epoxide, it could attack a carbonyl, right? Just think of it as an alkyne anion as a Grignard reagent. Can you explain the nucleophilic to electrophilic transition again? Yeah, so in this molecule here, every single thing is a nucleophile. This alkene is a nucleophile, this alcohol is a nucleophile. There is no electrophilic group here, right? Because there's nothing positive, right? This carbon is positive, but that can attack. So like that's not a carbonyl. When we attack it, we can't kick anything out. There's no good leaving group. So everything here is a nucleophile. Once we PCC this into an enone, this enone here is now electrophile, right? Where we have 2 electrophilic positions, the beta carbon of the enone and the carbonyl carbon of the enone, right? And then it depends on what nucleophile you have to attack. If you have a hard nucleophile, it will do a 1,2 addition, attack the carbonyl carbon. If you have a soft nucleophile, it will attack the beta carbon of the enone, 1,4 addition, conjugate addition, right? So that's nucleophile here became an electrophile by PCC. Yeah. Yeah, no problem. No problem. Yeah, good luck. Good luck on the final tomorrow night. Yeah. 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 No problem. No problem.
Thank you.
No problem.
Brian?
I heard you scored high,
Yeah.
Al. I heard you scored high. That's good. That's good.
Hey, Brian, I know you have to go. I just wanted to ask about one question real quick.
Yeah.
So I was doing one of Mariah's worksheets,
Mhm.
and I'm just gonna pull this up real quick. There was like an NA8. Yeah. It was aldehydes and ketones 5. It was the first problem on there. I don't know if you could pull it up on your end or. Yeah, so it was so we had like a 1, 2, 3, 4, 5. So we had an so we had like a 5 carbon chain, and then in the middle position, so like third carbon, it had like a carbonyl on there, and so it's symmetrical, right? If you could draw that, yeah, and maybe be
Like this?
I see. Okay, yeah, it looked like that, right? And so the first step was to add NaH, and then
NaH?
second step is ethylbromine, and then
Bromine.
third step is CH3CH2Br, and then third step CH3Li.
Wait, hold on.
Yeah, it's probably better if you erase.
This first step NaH, second step
So yeah, CH3, CH2Br.
CH3 CH2Br,
Right.
third step
And third step CH3Li. And then the fourth step
CH3Li,
was acid workup.
and then fourth step acid workup. Okay,
Yeah, right.
so
So I just want, yeah.
right.
So the thing I was confused about was that the NaH. So from like what is the reason we attack the alpha position and not directly onto the carbonyl carbon? Is it because we're not in acidic conditions originally? Like the first step
Yeah.
doesn't have acid involved?
Yeah, the first step is a very strong base. When
Okay.
you see H minus, that's a very strong base, which looks for the most acidic hydrogen, alpha hydrogen.
Okay,
Yeah.
I think I was getting
See
confused
you guys.
with
Good luck
I was
on the
getting,
finals tomorrow. Yeah.
yeah, so I'm pretty sure I was getting that confused then with like what we just learned with like the H minuses attacking the carbonyl carbons because they're hard nucleophiles. I think I was thinking of it like that.
Oh, right. So that hard nucleophile, soft nucleophile stuff, right, would be if this was an enone. That's not an enone.
Or okay. Oh, okay,
Yeah.
okay. Yeah, I was getting that part mixed up. Yeah, it's because I was trying to do it and then like I just get stuck after that. Like there's nothing you could do if you did that. Because
Yeah,
there's
right.
nothing to move around, right? Okay,
Mhm.
yeah, I was just confused about that. Okay.
Yeah.
Yeah, I think that was just a trick. All right, thank you
Okay.
though.
Yeah, no problem,
I
Amar.
appreciate
Good
it.
luck
Thank
on
you.
the final tomorrow. Yeah.
Thank you, appreciate it.
Yeah. No problem. Okay. Yeah.
This right? So like it attacks like right here. This attack.
Oh, right. So this halocane, both electrophiles, no reaction would happen.
Oh,
Right.
so-
This is supposed to be flipped.
wait. So how does this work?
Right. So the thing that was showing is that when we have an enone like this, any random enone doesn't matter, and we have an organocuprate, right? R2 CuLi, and the second step is R prime X.
Yeah.
Right. This is a soft nucleophile. Where does that attack? The soft nucleophile, the beta carbon. So let's use this to attack that beta carbon. Shift it over here, pop it over there. We're gonna get this here, where that's a new bond between the R and the beta carbon right there. Right. Now from the second step here, what is the structure here?
Oh, that's the enolate.
Enolate,
So,
right?
RX can only attack on enolates, but they can't attack enolates unless it's.
RX never attacks. RX is always an electrophile. It always gets attacked.
Oh, it gets attacked. Yeah.
It gets attacked, right? Where this is not the the alpha carbon. Reform that, and then this the one here attacks that thing, kicks out the X. Right. See ya. Yeah. Good night. See you, Tanya. Good luck tomorrow. Yeah, probably. Yeah, Tanya. Yeah. X, right? Then we go back down. The alpha carbon there attacks the R prime, kicks out the X to get that right there. If it was H3O plus, then it will go back down. The alpha carbon will get protonated by the H3O plus, and this will become a hydrogen right there.
Oh, so you replace this with
H3O plus, right? It will get protonated rather than have an R group. Right? If it was H3O plus, then that would be a hydrogen.
Oh, so if you ask like if you use like D.
Oh, D3O plus, then you can't put that in as invisible. You have to drop that D right there. Yeah, right. That's a good question. Yeah. Uh-huh. Yeah. Uh-huh.
So if you were to just RX or like what is it? So this is like a haloalkane. So they can't attack enones.
Right, because enone is an electrophile, and this is an electrophile as well.
Well, they'll only attack.
Yeah, grignard is a hard nucleophile that would attack the carbon carbon. 1-2 addition.
Okay.
Right. Uh-huh.
So
Yeah.
is there anything that would attack the alpha or no?
No, no,
No.
no.
So enone is like you just hands off alpha.
Hands off
because
alpha.
This is like a nucleophile. So can you do like electrophilic?
Electrophilic addition. In this example, no, because we can't make that go down and then like have that attack, right? But what you can do is you can deprotonate it using some kind of base like NaOCH3, CH3OH, where we have. Oh no, so this is a new booster actually, right? Where this is a strong base, and you know how we said earlier, this is a more acidic base because that gives us a more stable conjugate base. Make a double bond there, shift that there, and pop it over there, right? This is the resulting thing we get. Right. Where this is grab
Looks
that
like
H
it's like
to like, right? But it's very farther down the line, right? And if we just make that double bond there, shift this double bond here, and pop that double bond to oxygen, right? And then at this point here, you know how this was the alpha carbon? Now the alpha carbon is electrophilic, nucleophilic, I meant, right? And if we could bring in some kind of thing like that, where when we go back down, that star can attack this dot, pick up the Br, and then get this alkylated alpha carbon right here, right? But now the double bond is not between the alpha and beta carbon. The double bond is between the beta and gamma. That one changed. If you want to alkylate the alpha carbon, right, then your double bond would be right there. Yeah. No problem. Yeah. Oh, yeah. Let me try. Let me try doing that. Right. But I'll look at the key and then I can show you my thought process on this. Right. And then I'll check the key afterwards. I might be wrong, but we'll see.
A lot of the Leibniz ones are kind of cracked.
Correct. I know. The Leibniz has a lot of comprehensive reactions. Like he uses a lot of reactions from like all the chapters for what it should be.
What's worse is that some of the reactions don't work.
I
Like, I remember she tried doing H2KDC on an alkene. Like magically it didn't affect it. I was like,
I know. So some typos in Leibniz practice. Just like the discussion manual. Okay. Okay, so this is a 2-carbon chain. Let's say that 2-carbon chain is 1, 2. And let's say this is my 1, 2 right here. I'm just choosing that because like between these 2 carbons, there's a lot of groups there, right? So what I want to do is that since this is my 1, 2 chain right here, I can say that this came from an alkene. Like that. I'm just guessing because like when I see the alkene right there, I see an enone. And we work with a lot of enones in this new chapter, right? Where when we go backwards, right? Let's say we have a lot of R groups here, right? But first, let's just create this enone from this first. We wanna do Na NH2 to deprotonate the terminal thing. Second step will be I want that there, so I'm gonna react this with an aldehyde. And then third step, acid workup. Right, I'm just gonna draw this like this. This is the star atom. Dot atom. Star atom. Dot atom. Which is now an OH here.
Yeah.
Right. Since I want the aldehyde there, I'm not gonna use that methyl group because I don't want that methyl group there. Right. I want formaldehyde. Right. And then
also do the same thing with MCPBA, right? Not MCPBA, epoxide.
Oh, right, you can. Wait, hold on. Oh no, you can't because this is a new bond between them. It's one away, right? So it has to be carbonyl. It was 2 away than this epoxide. Right. So then from here, I'm gonna PCC it to get to the aldehyde I want. Right, and then I want to get the alkene from the alkyne right there. So I'm gonna use H2 Linois catalyst. Which will convert this alkyne into an alkene like this. Now we have an enone.
Oh, right there.
Yeah, and then like, you know how you can alkylate this with the Guman with these right here.
Yeah, how would you get the last method though?
Right. So we got to do this 2 times. So if you it doesn't matter which one you want to add first. Which one do you want to add first? Like it doesn't matter. Let's say we want to add this one first, right?
Yeah.
With the Guman, the second step would have to be like which one here? It doesn't matter. CH3 methyl group, right? But let me just show that to you. First step. Let's say this 2-group copper lithium. Second step, we don't have to. It's not acid, right? Because we don't want H there. Let's say it's CH3Br. Then that's gonna give us this. I'm just gonna put that up there and then this down there like that. Wait, let me see. This goes there. This goes there.
The double bond stays.
Oh wait, no, the double one does not stay. Yeah, because this would be like that.
Unless you could do LBA again, but then that would be very hindered.
Yeah. Right. So we don't want to do. Let's see. From here. Okay. Oh wait, hold on, hold on. Let's try this. Let's do this way. Let's set it that. I'm gonna try this. Okay, I'm gonna add this chain right away.
Oh, you're just
1, 2,
gonna
3,
like
4. 4.
it's like another NaH.
Yeah.
Then add the chain.
Yeah. 2, 3, 4. 2, 3, 4. Actually, let me just draw that regular structure. Aldehyde. 1, 2, 3, 4. I see it now. Now we could do I want the, it doesn't matter. If you do limits, that would be cis. I'm gonna use the sodium one, so then it looks nicer here. Yeah. 2 EQ, NH3 liquid, which creates this enone here, right? If you do Linois, then this would be up here, right? And then from here, I'm gonna do
Do the first step.
so LDA. I want to put that R group here on that beta carbon. What adds an R group on that beta carbon here? Organocuprate.
Like CH3, CH3, CH2.
Yeah,
BR.
1, 2, 3, 1, 2, 3, BR. Right, and then that's gonna give us.
I mean, what I'm thinking is like we could do the LBA and then like add a methyl
Yeah.
group because
Uh-huh.
this side doesn't have anything. So
Right.
I mean, even if it's like not very favored, it's
Uh-huh.
still gonna happen.
Yeah, it still can happen. And it does have to be LDA. It could be NaOR. Yeah, any strong base would deprotonate that alpha hydrogen, and then second step CH3Br. That's what's gonna happen. It's not gonna attack that carbonyl carbon because acid-base reactions happen way faster than nucleophile electrophile reactions.
Okay.
So we deprotonate this alpha hydrogen to make that negative charge. Negative charge attacks CH3Br, kick that out, get that group right there. Right, so this is the whole thing here. Can I see the key for this one? I want to see this is right. Like I messed up the first time, and I was like, what the heck is going on here? And then I went backwards and then tried something else, and it turned out to be okay, I think. Let's see. NaH, that thing, and then she did hydroversion oxidation on the terminal alkyne. Oh, and then she did self Aldol condensation, where this enolate here would attack itself to create that enone, and then she did the Guman from there. This is shorter, but that way works as well.
Okay.
Yeah, no problem.
Explain what you like showed me earlier. I got kind of lost.
Right.
It's like right here when you react it with Gilman, does it reduce it down to an alkane or no?
Wait, so the Guman here is the negative charge that's gonna attack that carbon. Yeah, that negative charge
Oh, okay.
R. And yeah, anything attached to the copper. Yeah, shift the double bond over there.
This right here.
Right, and then pop the double bond onto the
Oh,
oxygen.
okay.
Yeah,
And
right.
then later, how do you like repro? You like
Right, so then that would become an enolate right there.
Yeah.
Right, and then once we have that enolate, it could either get protonated or alkylated, depending on what you use. A double bond right there, where the alpha carbon is a base or a nucleophile. You could either add a hydrogen there or an alkyl group there. Right. If you use acid workup, then it's just gonna go back down and grab a hydrogen.
Oh, okay.
If you use RX,
Oh wait, so you do have to use H2O plus if you want to reduce it to alcohol.
yeah,
so-
right.
Okay.
Second step, H2O plus. Make sure to separate them though.
Yeah.
Yeah, right. Hey Marquez.
Hi, I have a quick question. So why can't I add this to the benzene?
This is not an acyl group, right? An acyl group has to be a chlorine attached to the carbonyl carbon. That
Because
carbonyl
Kevin was
carbon.
explaining that like intramolecular reaction would happen, but I'm like, why? Because like this is partially positive and so is that.
What?
Yeah, like why can't this just wait,
What?
why can't this
Oh,
that was our hypothesis. But like why does that matter? Why does it have to be here? Is that just part of the reaction?
wait, what do you mean? Like why does that have to be there?
Why can't I add this?
Oh, it
Okay, wait.
it could. There's both. Like,
What if I do like that? Can I add this?
yes, you can add that. You can
Because
add
the
that.
synthesis problem has like 5 steps, and I'm like, why? Or like 4 steps. They do something else, so I'm like, what the hell?
Look, it should just be 2 steps.
Yeah.
2
because then
steps.
you just do organic lithium.
Yeah. Can you show him? Can you show him?
No,
please?
but the enthalpy shows like
Okay, I'm gonna end the Zoom meeting now. Good luck on the final. Yeah.
For like fragments for like making the disconnection, is it always at like the alpha carbon you would recommend doing that? Like the C
Um,
lim carbon limit?
It's alpha cleavage if you have an oxygen and nitrogen. on the molecule. If there's an alkene on the molecule, it's beta cleavage.
Okay. Thank you so much, Brian.
Yeah, no problem, Isabel. Good luck tomorrow on the final.
Thank you. Bye.
Yeah, bye. Okay. Yeah. See you, Zinyan. See you tomorrow. Oh, like, good luck tomorrow. I mean, good luck tomorrow night.
Yeah, thank you.
Yeah, no problem, Zinyan. See ya.
Bye.
Bye.